right, we need to finish this packet. We may not do it all in one video, but we need to make some progress. Anyways, here at the bottom of this next page in the notes, you'll see a topic that's going to come up fairly frequently this year. So it's going to be important that you are comfortable and familiar with questions like this, because it's going to come up quite a lot. So anyways, here we go. It gives us the graph of the function f prime of x. So it gives us the derivative graph. And then it's going to have us answer questions about the original function. Now be really careful. If it gave you the graph of f, answering questions about f would be easy. Like for instance, that previous question, it said here's a graph of f. And from it, I could answer all sorts of things. Like, hey, I could figure out where I have a minimum. I could figure out where I have a max. I could figure out where the function is increasing. I could also see where the function is decreasing, right? That's all pretty easy. If you have the graph of f, answering questions about f is very simple. But we're not usually going to have the graph of f. A lot of the times, we'll have the graph of f prime. So how do we answer questions about the original function when I am given the graph of the derivative? You're just going to have to follow the logic. It's not super hard, and I hope over the course of the year this will become something that's very easy for us, but it can be a little bit strange at first, so please make sure you're paying attention. It says, use the graph of f prime. Always pay attention to what the graph is labeled as, but use the graph of derivative to answer questions about f. We're going to find the x values, the intervals, or the points, where f is increasing, decreasing, constant, and where it has any extremas, so where it has any maximums and where it has any minimums. Okay, so let us go for it. Let's do increasing first. Check it out. If I want f to be increasing, f is increasing. Increasing means going up. Going up means the slope is positive. If I want the slope of f to be positive, that means the derivative is positive. The derivative is the slope of the original function. So if you want the original function to be increasing, to go up, to have a positive slope, that means you are going to have to look and find when the derivative is greater than 0, when it's positive. So from this derivative graph, you would be looking at when it is above the x-axis, right? Positive is up above, negative is down below. So f is going to be increasing when f prime is positive, and then here we go, we can write those answers. This interval, negative infinity to 8. And then the next interval would be from 0 to b. And then the last interval would be from b to infinity. It wouldn't really be wrong if you just said 0 to infinity, that's okay. But remember, increasing means the derivative is positive. At this point, the derivative is not positive. The derivative is 0. So I probably would split that up, and I would have the two intervals. Hey, it's positive between 0 and b, and then it's positive after b. But I would not include the b in this interval. Like, I wouldn't smush those together and say 0 to infinity. A lot of the times the AP exam may have those kind of combined together. But I like to answer things that are a little bit more logically worded. Your function will be increasing when its derivative is positive. That means where is that derivative graph above the x-axis? Above, not on, not below. Okay, well let's do this something similar to get decreasing. F would be decreasing when the derivative is negative. Right? Decreasing means going down. That means that graph of f, which you cannot see, but we're still answering questions about, the f function would have a negative slope, so that means your derivative is negative, which means your derivative graph is beneath the x-axis. Your function f is decreasing when its first derivative, f prime, is negative. And I can quickly and easily tell when this graph is negative. It's below the x-axis. So that one would be from a to 0. Right, so if you're looking at the derivative, you can still answer questions about f, and we can answer a lot of questions about f, and as we go through this year, we're going to learn more and more and more that we can tell you about f, but just be careful. The really common mistake is for people to say, oh, f is increasing from j to k, and it's increasing from b to infinity. Well, you have to be careful. This is not the graph of f, so don't answer questions very directly. There still is a way to get those answers, but you have to think about it. If you want f, the function that you cannot see, if you want f to be increasing, that means the derivative, which is the function you can see, you want that derivative to be positive. So you'd be looking for any intervals where that derivative is above the x-axis, and decreasing correspondingly is where the derivative is negative. So just be careful. You can answer the questions about f, but you have to think a little bit more than just, oh look, it's going up. No. If you're given f, it's that easy. If you're given f prime, you have to think. Okay, let's see the next one. F is going to be constant. Oops, can't spell. F is going to be constant. By the way, you could write INC for increasing, or you could do DEC for decreasing. A lot of the times I'll just do the up arrow or the down arrow because I'm lazy, but that's okay. But here, increasing is when the derivative is positive, decreasing is when the derivative is negative. Constant means your line's going to be horizontal, so f is going to be constant when the derivative is equal to 0. Now, there's not usually intervals where this happens. There's typically only points, instances where this happens, and it's going to be any of the x-intercepts of that derivative. So therefore, at x equals a, x equals 0, and x equals b. Okay, so those hopefully should be okay. Increasing means the derivative is positive, so where is that derivative graph above the x-axis? F decreasing means the derivative is negative, so where that graph is below the x-axis. F being constant means the derivative is exactly equal to 0, which happens when that f prime graph crosses and or touches the x-axis. Okay, now the next one's a little bit harder. We're going to use this information. Remember, increasing is going up, decreasing going down, constant means doing neither. We're going to use all that information to answer questions and figure out where does f have a maximum or where does f have a minimum. And again, we're only looking at the x values. Okay, so try to follow this logic. Let's do the maximums first. Your maximum, it would happen, hey, like if f, probably shouldn't put this arrow because you're gonna get confused. You're gonna have a maximum when f changes from going up to going down. Right? That's what it means to be a relative or local maximum. Your function was going up, but then it stops and it turns and then it starts to come back down. Right? I think that hopefully it makes sense. You have a maximum when the function changes from going up to going down. The more precise language is changes from increasing to decreasing. That's great. Now, if this graph was labeled as f, you could easily see where the maximum is. But remember, that's not f, that's f prime. So we somehow have to figure out how I can answer questions about f prime. So let's see, I know I'd have a maximum when f changes from increasing to decreasing. That means the derivative, aka the slope, is going to have to change from positive to negative. If your slopes change from positive, going up, to negative, going down, then that instant, when it changes, is going to produce a relative maximum. Right? So you're going to have a relative maximum when your function changes from increasing to decreasing. That means, put the little 3 dots, that means therefore your derivative changes from positive to negative. All right, so let's go ahead and answer. Therefore, that is going to happen at, let's figure out, I think there's one point on this graph where the derivative changes from positive above to negative below, and that's going to happen right here at A. Right? The derivative is up above, but then it crosses over and is now down below. So you have a max when f changes from increasing to decreasing. That's not going to be at k because that's not the graph of f. If f changes from going up to going down, that means the derivative changes from positive to negative, and that only happens right here at the x-intercept where it crosses from above to below. Okay, let's see if we can do the same thing for the minimums. You know your function f would have a relative minimum when f changes from decreasing to increasing, right? If your function is going down, but then it stops and it turns and then it begins to go up, well, that turning point would be a local minimum or a relative minimum. So we know f is going to have a relative min when f changes from decreasing to increasing. Please don't say at k. That's definitely not going to be right. Please don't say B. That's also not right. Please don't say J. That's not right, because that is not the graph of f. Please be careful. You know the original function would change from decreasing to increasing, but you can't see the original function. So we have to think about, okay, logically, what does that mean about the derivative? And if f changes from decreasing to increasing, that means f prime, the slope, changes from negative to positive. And there's only one place on this graph where that happens. Therefore, at x equals 0. Oops, sorry, x equals 0. Okay, so think about it. At a, the derivative changes from positive to negative. That means you had a positive slope, changes to a negative slope, so I know that's a max. At 0, the derivative is negative, so that means your original function was decreasing, but then the derivative crosses, and then the derivative is positive. So at x equals 0, not a max, you're going to have a minimum. Let's look at what happens at b, because that was another one of those special points, right, where the derivative is 0. Here you can see the derivative was positive. The derivative was positive on the left side of b, and the derivative is positive on the right side of b. So your function f would be increasing, then it would be constant for that one moment, and then it would be increasing again. You'd have a graph that would look like this, where it's going up, it's constant, and then it's going up again. That would be neither a max nor a minimum. Right, so in general, those x-intercepts of your derivative, those are the values where your original function f could have an extrema, either a max or a min. And how it's an x-intercept matters. If it's an x-intercept but it doesn't cross, like here b was, then it's neither a max nor a min, because the slope doesn't change. If it's an x-intercept and it crosses from below to above, negative to positive, that means you had negative slope, decreasing, then it changes to positive slope, increasing. If you change from going down to going up, you know that's going to produce a relative minimum. And then if you have an x-intercept for your derivative, that changes from above and it crosses to below. Well, if your derivative changes from positive to negative, that means you had positive slope, or increasing, change to a negative slope, and that's going to generate a relative max. So just be careful, kind of conceptual, a little bit heavy. Hopefully it makes sense. If not, we're going to keep working with this over the year, and hopefully it'll eventually make more and more sense. But you can use the graph of the derivative to answer questions about the original function. But it's not as easy as saying, oh, look, there's the max. Oh, look, there's the min. No, you have to think a little bit more about it. Okay, let's flip it over, move on to the next page. And then you probably just pause it and end this video after this, and I'll do another video for the last page. Okay, let's see here. We've got let f be a function which satisfies f of 2 plus h minus f of 2 equals 5h minus 3h squared plus 9h cubed for all real numbers h. Find f prime of 2. And you're like, oh my gosh, Mr. Bell, what in the world are you talking about? Well, let's kind of connect it back to some stuff that we should know. It says find the derivative of f at 2. So let's go back to that very fundamental basics. What is your derivative? Well, your derivative is the limit as h is approaching 0, and you have f of x plus h minus f of x over h, right? That's your difference quotient. That is how you can find the derivative. That's your limit definition. Now here, it doesn't just want the whole function, right? It says, in particular, I want the derivative at 2. So I know f prime of 2, it's going to be the limit. As h is approaching 0, you have f of 2 plus h minus f of 2 over h, right? That's what the derivative of f at 2 would be, right? This difference quotient limit. All right, so let's see if we can somehow plug and chug and see what we can work with from this point. And notice here in the numerator, or here in this question, you see this chunk that is going to correspond to that numerator of the difference quotient. Like I've got f of 2 plus h minus f of 2, like all of this is equivalent to what's written in this numerator. But I probably don't want to write it like this, but what I can do is I can make a substitution. And all of this stuff that's in the top, instead of having it as f of 2 plus h minus f of 2, I can change all of this stuff in the top into what that is equivalent into. So let's go for it. We still have the limit as h is approaching 0, right? I'm not changing the limit yet. I'm just changing all the stuff in the top. And instead of this left side of the equation, I'm going to rewrite it as the right side of the equation. 5h minus 3h squared plus 9h cubed. All that was still over h. Okay, now that looks a little bit nicer, right? At least there's like a little bit more kind of solidarity about it. Now you see, you still got all these h's. If you tried to plug it in right now, you would get 0 over 0, which is indeterminate. So we need to do something. But luckily, now everything in the top has an h. So now I can go through and I can reduce it all by an h. So here we go. Still have the limit as h is approaching 0. Reduce everything by an h, right? That's going to cancel from the bottom. That means 1h is going to cancel from every term in the top. So I would have 5 minus 3h plus 9h squared. And then at this point, we could go ahead and evaluate it. I could plug in all the h's that are left, plug them in as zeros. So I have 5 minus 3 times 0 plus 9, 0 squared. Well, I hate to break it to you. 3 times 0 is 0. 9 times 0 is 0. So then I end up getting this answer as 5. Seems a little bit annoying, but it's actually a fairly simple question, right? And that was my derivative at 2. Seems a little bit weird, but you're just starting with your fundamentals, starting with your limit definition of a derivative, plug in your x value as 2, and then here hopefully you should recognize that all this stuff, that's what the question was kind of handing to you on a silver platter. You just change all that stuff into the terms with h's, and then you can go ahead and evaluate it. Hopefully it makes sense. Next one's going to be a little bit harder. Kind of the same setup. It says f of x plus y equals f of x minus 4fy plus 9xy for all real numbers x and y. And suppose that the limit of f of h over h as h goes to 0 is 2. Use the definition of derivative. That one's nice. It really tells you like what to start as. So I know that limit definition. Let's go for it again. I guess I should write f prime of x is equal to f prime of x is equal to your limit as h is approaching 0, f of x plus h minus f of x over h. That is your limit definition, and it's telling you straight up, start with that definition. So let's see if we can somehow connect the dots, and let's see if we can get an answer. Now, in this question, it doesn't have x's and h's, right? It has x's and y's. So that's a little bit annoying, but, you know, it's just a variable. X, y, h, they're all just variables, right? They represent arbitrary, like, kind of placeholders. So if you don't like y's, change them to h's. Like, it doesn't matter. As long as you change all of the y's into h's, right? You can't just change some of them and then leave y's. It's y is a variable. It doesn't matter what it is. You can change them to lightning bolts and smiley faces. It doesn't matter. I don't care. But here, we are used to working with x's and h's. So I'm going to go back to this, and I'm going to switch it so that instead of x's and y's, I'm going to switch it so that it has x's and h's. So here I have f of x plus h. I'm just changing the y to h. That would equal f of x minus 4, oops, I forgot the 4, equals 4f of h plus 9xh, right? If you don't like it with x's and y's, that's okay. Switch it to x's and h's. It doesn't matter, as long as you switch all the y's into h's. Okay, now let's see. The previous question was a little bit nicer because we had this difference in the top, right? We had that, and then the question straight up told me, hey, all of this stuff that was in the top, all of it right now, right off the bat, can just change into this easier expression. And you can just substitute it the whole top. Well, the second example doesn't quite have it for you exactly, right? I've got the f of x plus h. So if you wanted to, right, this will work. You could take all of this, and plug it in right here, right? Since you know f of x plus h is equal to all of this, these three terms, you could take this whole expression and plug it in this top left piece. That will work. Or if you wanted to, I could, right, you see here in the numerator, we have f of x plus h minus f of x. I could just take this f of x and I could move it over. And then I'd have f of x plus h minus f of x. That would be negative 4f of h plus 9xh. Kind of getting off the screen. Oh, I'm definitely off the screen. Sorry, let me zoom it out. So again, you could do this two ways. You could take this f of x plus h, you could take only this part, and you could change it into all of this, right? So you could take all three of these terms, you could plug that in right here, and then the f of x's will cancel. Or if you want, you can bring the f of x over, and then you can make this substitution now, that's the whole numerator like it was on the previous example, and then I could change the whole numerator into that other stuff. So I still have the limit as h is going to 0. Instead of all of this numerator, I'm going to make the substitution. I have negative 4 f of h plus 9xh over h. So that one was a little bit harder, right? It's definitely a step up from the previous example. A, it had x's and y's instead of x's and h's. Hopefully you feel okay. Just changing all the y's to h's. Like that really shouldn't make a difference. And then B, the thing that probably makes it a little bit harder, was it wasn't handed to you. It wasn't presented perfectly for you, so that the substitution was perfect right off the bat, right? But you could, if you wanted to, you could just take all of this stuff and plug it in for the one part that it's equivalent to, or if you just take what it gives you in that original equation, in that original question, you could just rearrange it so that you create what the numerator of the difference quotient is, and then you can make the substitution. But you got some extra algebra, right? So it definitely makes this question harder. Anyways, let's continue forward. Now, you can't divide by h, right? A lot of times students will go, oh, look, Mr. Bell, that's gone, it reduces. No, that's not how it works, right? You would have to reduce everything by an h. And this term, that h in the parentheses, that doesn't count, right? That's inside. That's the function having been evaluated. You would need an h out there with the 4. So you can't reduce this thing by h. Instead, what we can do is we can split it up. And we can use some limit properties. It's still going to be the limit as h is approaching 0. But I could have negative 4 f of h over h plus, and then we could have the limit as h is approaching 0, 9xh over h, right? That's definitely a thing. If your denominator is one chunk, you could split up that fraction. You could take, hey, this plus that, right? That is not going to break any rules of algebra. That's fine. Now let's take that negative 4, let's factor it out to the front. And I have f of h over h plus, and look at that, that's going to reduce. So you have plus the limit as h is approaching 0 of just 9x. All right, well, let's see what we got. All of this stuff right here, do we know what that is equal to? Because the h's still don't cancel, but do I know what the limit as h approaches 0 of f of h over h is? Yes, right? In this question, it told me specifically, if you have f of h over h and the h is going to 0, it specifically told me that all of that chunk is equal to 2. So there you go, that chunk right here. Question told you, plug it in, was 2. Now here, all the h's canceled. If you had any other h's, those h's would change to zeros, but you don't. All you have is the 9x. So now we're pretty much done, right? We are going to get, therefore, this derivative function. It's going to be 9x minus 8. It's certainly harder than what the previous example was. You had to do some extra algebra. You had to switch the y's to the h's. That shouldn't hopefully be a problem. But then you had to do a little bit of extra rearranging or some extra substitutions and canceling. This one's definitely harder. And you also have this little fact that, hey, the f of h over h, it told me that specific little fact that limit was going to be 2. So just always be on your lookout. Like it's conceptually testing the same thing. It's still wanting you to do this question, which is testing the limit definition of a derivative. The fact that this has some extra algebra in it should not really be the reason why you miss it. I can see how it would make it harder, more annoying, more tedious, yes, but it shouldn't be the reason why you miss the question and get it completely wrong. All right, so just be careful. And always be cognizant when you read a question, if it tells you 2 pieces of information, like, hey, it told me this equation, and it also told me this little fact. The AP exam is really good about not giving you extra stuff, right? So if it tells you 2 little facts, or if it tells you 2 pieces of information, you should expect to need to use both of those pieces of information. Like, if this wasn't important to you solving the question, they wouldn't have wasted the ink to type it and to put it in there. Right? So always just be on your toes. If you see something given to you in the question, you should 99% of the time expect to need to use that. Like it should come up somewhere in your question. If not, you're probably doing something wrong. Right? It doesn't usually give you extra stuff. It'll always give you enough. I know sometimes it'll feel like it's not giving you enough, but it will always give you enough, and it very rarely ever gives you more than enough. It rarely gives you extra. So if it tells you 3 things in the question, you should really expect all 3 of those things to come up. If it gives you 5, you're probably going to need to use all 5. All right, so just always be on your toes. All right, last part for this video, then we'll end it and we'll shift it over for the next one. The next one will be about derivatives using data, which will be tedious and very calculator dependent. But here, let's finish this one, and we'll get it uploaded. All right, given limit as x is approaching 5, f of x minus f of 5 over x minus 5 equals 3. So it gives me that limit statement. Which of the following must be true, might be true, or can never be true based on this piece of information? All right, let's see. What is this piece of information that it tells me? It says this limit, f of x minus f of 5 over x minus 5. Wow, that looks a lot like a slope. Looks a lot like the slope between 2 points, one of them being arbitrary at the point x, and then the other one being very specific where x has been plugged in as 5. So that looks like a secant slope between 2 points, x's and 5's. And then here, take the limit, and you send x to 5. So it takes the secant slope, and then that limit process is going to compress the 2 points down to 1. That's your alternative version of the limit definition of a derivative, right? All this is right here. This literally, right, all this stuff that I'm like circling and kind of crossing off, that tells you the derivative at 5 is equal to 3. Right? It doesn't straight up hand you that derivative for free. It gives you the limit definition, and then you're expected to be able to recognize that this means the same thing as this, right? It's just your limit notation for your derivative as opposed to the apostrophe, the prime notation. But here we go. That's all we know. The slope of f at x equals 5 is 3. If I were to draw a tangent line, I don't know what the f function looks like, but if I were to draw a tangent line at 3, at 5, the slope of that tangent line would be 3, right? We know the derivative of f at 5 is 3, so I know what the slope is at that point. Now let's go ahead and see, okay, based on only that information, which of these following statements must be true, might be true, or can never possibly be true. Let's look at them. Part A, f prime of 5 equals 3. Oh, well, yeah, that's literally what the question gives you, right? It just gives you the limit definition as opposed to the more calculus notation. But for sure, this one must be true. The slope of f at 5 is 3. Yes, that must be true. That's verbatim what it gives me, right? Very nice. Okay, here we go. The slope of f at 5 is 0, right? It says the derivative of f at 5 is 0. No. Like, the derivative is a function. If the slope is 3, the slope can't also be 0. That's not possible. This one's never. We know the derivative value at 5 is 3. That means it cannot be anything else, right? The derivative is going to behave as a function. It'll only give you the one output every time I plug in 5. I know the slope is 3. That means it can never also be 0. Can't have a slope of 3 and a slope of 0 at the same point. Like, that doesn't make sense. All right, next one. It says f of 5 equals 3. That means, hey, is this graph going to go through the point 5, 3? I don't know. I know the slope of f at 5 is 3. I don't know graphically where the function is located. Like, I don't know the y-intercept. I don't know any of the x-intercepts. I don't know really any of the placement of this function f. All I know is the slope at 5 is 3. I don't know where that physical point is. I don't know where the y-coordinate is. So this one is might. It's quite possible that the graph goes through the point 5, 3, but there's infinitely many other y values that this graph could go through. That would also be equally as possible, right? So it could potentially go through that point, but I don't know. I certainly don't know. Right, so that one might be true. Could be true. It's probably not, but it could be true. All right, part D. F is continuous at 0. I don't know anything about x equals 0. All I know is the slope of f at 5 is 3. Could it be continuous at 0? Sure. Could it have a point discontinuity at 0? Sure. Could it have an asymptote at 0? Sure. I literally don't know anything. I'm like Jon Snow in Game of Thrones. I know nothing, right? I don't know what's happening at this function when x is 0. I don't know. I don't have any information. It might be continuous. It might be discontinuous. I don't know. All we know is the slope at 5 is 3. Right, part E. F is continuous at 5. No, now 5 is actually an x value that I know a little bit about, right? I know the slope of f at 5 is 3. I know the derivative at 5 is 3. I also know, if you remember back, it wouldn't be possible for the derivative to exist if there was a cusp, or if there was a sharp turn, or if there was a vertical tangent, or the fourth one, if there was a discontinuity. So I was given, hey, Mr. Bell, hey, the derivative exists. Well, if I know the derivative exists, yeah, I know what the slope of the graph at that point is going to be. But I also know it has a slope, right? That means there weren't any of those weirder issues. I know since the derivative exists, it is not possible for there to have been a cusp at 5. And it's not possible for there to have been a hole at 5. It's not possible for there to have been a vertical tangent at 5. Or a sharp turn, right? Since the derivative exists, I know none of those 4 issues came up. And discontinuities would have been one of those 4. So this must be true. And this is an important statement, right? If you have the derivative, right? If you know the function is differentiable, then 100% of the time, that is also going to imply continuity. If you know it's differentiable, so if you know the derivative, the slope exists, then you also know 100% of the time, every single time, that function is continuous at that spot. It might be discontinuous elsewhere, but I know at that spot it's continuous. Now, the reverse isn't necessarily true. Just because it's continuous doesn't necessarily mean it's differentiable, because you could have something like this, like a sharp turn. That's continuous, but then that would not have a slope, or like a cusp. That would be continuous, but it would not have a slope, or you could do a vertical tangent. So if you know it's continuous, that doesn't guarantee that it's going to be differentiable. Could be, but it may not. If it's differentiable, then 100% you know it's going to be continuous. So must be true for part E. And then the last one, it says the limit as x approaches 5 of f equals f of 5. This seems kind of weird, like, Mr. Bell, why? I'm so tired of limits, Mr. Bell. Well, I mean, this question and this question, parts E and F, they're literally the same thing. But on part E, it gives you the word continuous, and then on part F, it gives you the mathematical definition for continuous. Remember, continuous, there's 3 things that have to be true. The function has to exist, the limit has to exist, and then the limit has to equal the function. Right? Those are the 3 things that you need for a function to be continuous at a point. This is just the 3rd one. It says, hey, Mr. Bell, f of 5 exists, the limit exists, and those 2 things are the same. These 2 are asking the exact same thing. Right? F is continuous at 5. It's just asking you in words in English, is it continuous? Yeah, it must be, since the derivative exists. This is also asking you if it's continuous. It's just asking you with the mathematical definition as opposed to the English language word. Right. And yes, since I know it's differentiable, that means it's continuous. That means f of 5 exists. Right? It wouldn't be possible to have a derivative if there was no point. Right? Well, it wouldn't make sense. That also means your limit exists. Now, that limit exists kind of carries a lot of weight. That means your limit from the left exists. It means your limit from the right exists. And it means those 2 things are the same. Right? And it also means, hey, your f of 5 equals the limit as x approaches 5. So this statement, if you know the derivative exists, it kind of tells you a lot. You know that it's continuous, so you know there has to be a point. You know there has to be a limit. And if there's a limit, that means both of the individual one-sided limits have to exist. And then specifically, you know the overall limit must equal the function value, must be true. Right? This is continuous just as much as part E is continuous. This just uses the word, this uses the mathematical definition. But yes, since the derivative exists, then I'm 100% sure that the function is continuous. That means there was a point, f of 5 exists. That also means there is a limit. The limit as x approaches 5 exists. This means the limit from the left and the limit from the right equal each other. And then specifically, since they're continuous, I know the function has to exist exactly where it is supposed to exist. So must be true. All right, hopefully that makes sense. I'll see you guys in the next video.